Thanks for coming to my talk. We actually do have a doctor in the house. If there's any, I've had people, of course, try to fake a heart attack to get out of my presentations before, so it won't work so well this time. There's someone who will attend to you and make sure you can be resuscitated in time to participate in the remainder of the talk. So my name is Robert Secord. I'm pretty well known for some books on secure coding and C and C++ and work on the CERT Oracle secure coding standard for Java. Probably more of a C expert than a Java expert. I've been a member of the C Standards Committee since about 2004. So if you want to catch me in the hallway and throw things at me because I was responsible for, at least partially responsible for that, I'll understand. Currently, I'm a director at Technical Director at NCC Group. Most of what I do is develop and deliver secure coding training in Java, C, C++, and C#. So this is actually an excerpt from my secure coding in Java training class. When I'm not doing that, I'm doing research, which typically involves, this work came from some of that research. And I also do consulting work for clients, usually security analysis of their code bases, just to keep my hands in it and keep seeing what kind of mistakes people are up to these days. And it turns out it's mostly more of the same. So quick refresh on Java serialization. Java object serialization supports the transformation of a graph of Java objects into a stream of bytes that can be stored or transmitted. So basically an object is serialized into a byte stream that might be stored in a file, a database, or just temporarily in memory, and then is deserialized from that form back into the original objects. So one thing, this is almost always a graph because whenever you have a single object, it usually has some other objects defined within it, and so to reconstitute that object, you have to serialize the entire object graph and then deserialize that again. How many of you use serialization in your job? Okay. And then there's probably the rest of you who do use serialization but aren't aware of it, would be my guess. So just to do a quick example, we're going to serialize a bicycle object to a file. This is very simply done in Java in 4 lines of code. So we create an output stream, which in this particular example is a file output stream. And we then decorate that file output stream object with a object output stream. We then invoke the write method, so we're going to create a new instance of this bicycle class and basically say, it's got 1 wheel and, we're going to call it a unicycle. So that's it. That's the whole, that's all the code to serialize an object. It's quite simple. And there's nothing actually wrong with this code. It's perfectly correct. But still potentially, not the serialization so much as deserialization, still quite potentially vulnerable to attack. So to deserialize that, we basically reverse the process. So we create a file input stream. So this is an input stream object, and in this case, we're going to read this from the temp file. So the input stream object will provide the source bytes in order to deserialize this object. We'll then decorate the input stream with an object input stream object, and then we'll invoke the read object method of the object input stream class. And read object is just gonna return an object. And so, typically what will happen here is that we would, I'll get my fancy pointer up here. Is that we would cast this to the object that we're expecting, which in this case is a bicycle. So developers can implement methods to customize how objects are serialized and deserialized. There's a write replace method, which provides a replacement object to serialize. a write object method, which really gives you full control over writing the stream. So if you were to implement a write object callback, you could basically preserve an entirely different object. You wouldn't have to use any of the actual fields that were defined for that object. You could write whatever you want. And during deserialization, there's a read object method, which again gives you full control. But of course, that corresponds to the write object method, so you're going to want to read the things in that you wrote out with the write object. Read resolve, which will replace a deserialize object with another object. And finally, a validate object method, which will validate the graph integrity after it's been deserialized. And the write, replace, and read resolve are really to implement a serialization proxy pattern where, when you design an object, it's designed for some type of runtime property, right, to execute efficiently and so forth. It's not designed to store well, right? And so frequently a proxy pattern makes sense because then you can implement it to run fast, but then you can write a proxy, a kind of replacement object, which optimizes how it's stored for serialization purposes, right? So if you think about that for just a second, it makes a lot of sense. So during serialization, the write replace method's executed first. If present, the write object method then operates on the replacement object. During deserialization, the methods are called in the reverse order. So the read object method's called to read in the potentially the replacement object if it's there. And then the validation methods that can be executed on the replacement object, not on the proxy object. Any proxy object would be silently discarded. So when you look at the deserialization process in a UML sequence diagram here, the application code that we saw earlier for deserializing a bicycle, that will run. It will get the bytes and then initialize the object input stream and call the read object method. So that will transfer control to the object input stream class. It will resolve classes it finds in the stream using the resolve class method. And that's basically the same process that JVM uses to load any class that you're going to use. And then it will begin to deserialize the objects. And of course, again, any single object is probably a graph of objects because it's very unusual to just have an object with no objects inside. If the callbacks are defined, the read object callback will be invoked to restore object member fields. The read resolve method will then be called to replace the restored object, and then again, a validate object will be optionally called to validate the graph. After that, after each object is called and all three methods are executed for each object, when defined, the read object method will return. And as we saw earlier, typically what the user will do is then cast that deserialized object to the expected type. Sometimes when you're writing this as an abstraction, you'll just read it as an object, so you can have one function that deals with every single case of deserialization. And then you go ahead about using that deserialized object. And then a bit that's sometimes forgotten is eventually the finalize method will be called for that object. And, a little bit of legacy stuff there, but. So naive use of object serialization can allow a malicious party with access to the serialization byte stream to read private data or create objects with invalid or dangerous state, and probably a bit worse. And, kind of the one slide explanation of the problem with Java serialization is, this guy here who accidentally cut off his hand while trying to slice a sandwich. He could probably successfully implement Java serialization, right? It's not very hard. But the effort to implement it securely is really quite difficult. So I have a full day class I teach on this, and the actual material doesn't fit into a full day. And so it's a very complex topic. There's a lot of researchers who work on this. Most of them cover about 40% of this. The whole issue about how you do this securely is quite challenging problem. So just to reflect that, the secure coding guidelines for Java SE, not the ones I wrote, the ones that Oracle wrote, they put this very serious looking warning on their page to talk about deserialization of untrusted data is inherently dangerous and should be avoided. There's some rumors that Oracle would like to get rid of serialization. I'm sure they would. The problem is all the legacy code that depends on it, and it's everywhere. So I could see them maybe providing a more secure option, so that would be a good start to eliminating it. So default serialization of an object writes the values of all object fields to the serialization stream. And right away, you can see why that might be an issue for security. It writes out all the private fields, package private, protected, and public. So if you were thinking that somehow declaring a field private was if that was part of your model for securing this object or, preserving the integrity of your customer's data, this suddenly becomes an issue. So any serialized private data that's stored in a file or transmitted over network can be leaked. So once you serialize this private data, now you have to think about everywhere that goes and how you're going to protect it in every form it takes. And some people will serialize cookie data onto a client website, and then it's pretty darn easy to reverse that and just put whatever you like in. I mean, my favorite thing to do is I'd like to take the cookie from my bank account and take my name off and put Bill Gates in because he's better funded than I am, generally speaking. Again, malicious code can read a serialized object's private fields by just simply serializing the object and then examining the bytecode that gets generated. So CWE, which is MITRE's common weakness enumeration, they cover all this under deserialization of untrusted data. Here I'm talking about Java serialization. I have a 40-minute talk on Jackson JSON, which basically it's just about as dangerous. So most of these, serialization, deserialization technologies or marshalling and unmarshalling technologies all seem to be sort of exposed to the same sort of problems. And the very simple description of the problem is that, when you deserialize objects, basically, you're from an untrusted source, you're basically allowing an attacker to tell you what code the attacker wants you to run. And so this boils down to, how do I securely run code supplied by an attacker, which is potentially the most difficult problem in security. So the consequences vary depending on which objects are deserialized and how they're used. We hit briefly on confidentiality, this very simple ability to leak private fields. The integrity, attackers can modify objects or data that's assumed to be safe from modification. They can certainly modify the private fields, right? Because all that data is just stored in the file along with everything else. They can create objects that have inconsistent state or impossible state, break the invariance. You really have to trust the source of this data, right, that it hasn't been modified. These very prone to denial of service attacks. The very simplest denial of service attack is the attacker creates an array of int max size, and that turns into a out of memory error immediately upon deserialization. And of course, remote code execution, which we're going to look at an example of. So a simple, unrealistic remote code execution example is that we have a serializable gadget, and we have a private string command. And then we have a read object method, which is going to basically execute this command, right? So I say unrealistic and simple because it looks unrealistic and simple, but trust me, people have done this and deployed this, but I still have to call it unrealistic because it just seems too dumb to be true. Clearly what, so there's a mode, the developer's thinking of about how this is going to be used, which is valid, right? So they're thinking, I've got 3 or 4 methods which can set this private command string to certain specific commands, and I know that all those commands are safe and they can safely be invoked. And what they're not considering is serialization, deserialization, right? So this gets, serialized. The attacker edits the file. This is a string, so they probably don't even need any sophistication to edit the file. They change this to some sort of command which is going to root the system it deserializes on. As soon as this thing gets deserialized, this attacker-supplied command is executed, and they've got they own that machine. So serialization has been around since Java 1.1. I think that's like 92 or 91 or something like that. It's been around probably longer than a lot of you have been programming. I'm going to skip the old jokes. Sometimes I make old jokes, and then, because I'm old, and then I actually offended some people by, lumping them in the same boat with me, which, it's kind of horrible. So anyhow, there's a bunch of protocols, formats, and products which are then layered on top of Java serialization, including remote method invocation, Java messaging, HTTP to some degree, WebLogic and Xstream, and this whole problem of serialization blew up big a few years ago when people all of a sudden realized that their WebLogic installations were running on top of Java serialization, and they were susceptible to these sort of exploits. So all this is really bad. Again, Java deserialization is susceptible to vulnerabilities in code that really appears to be defect-free. That code I showed you earlier, which there's no better way to write that really, is still vulnerable to attack. So typically what happens is an attacker could serialize an instance of an unexpected class and then send it to some service that would then deserialize this malicious object. So before, we wrote that code expecting there to be a bicycle object, when we called read object, but it could be any kind of object, right? You're just expecting it to be a bicycle object. So your code is likely going to cast that to an expected type. That would typically allow Java's type system to ensure valid object trees. But by the time that type checking occurs, it's already too late. Basically, by the time the read object method returns, the exploit has completely, has completed execution, and all the damage has been done. So this is too late in the process to fix the problem. So again, if we look back at our deserialization process, part of the issue here is these various methods which are going to be called during deserialization, and what these methods, what sort of actions they might perform. And in the 8-hour version of this class, a quick sort of response is, what if I don't write any of these callback methods? That actually turns out to be worse. So to code this securely, you do typically need to take advantage of these methods and sort of non-trivial objects with invariance. So just not writing them is not a solution. Okay, I'm going to do a quick demo, and this is going to show remote execution from deserializing a gadget chain that uses the Apache. I'm going to pronounce that as Zalon. If anyone feels it's pronounced differently, let me know later. So let's go ahead and take a look at that. I actually started debugging it before class. I thought I can save 3 seconds, but little did I realize I would use more than that time explaining to you about how I saved all that time. A couple people laughed. Okay, so let me single step into this. Let me step into this. And what we want to do here is look at the RCE payload method. So we're going to create a, we're going to call this gadget create templates impl, which is going to create our gadget chain. And the target of our exploit here is just to launch the calculator. You'll see in a minute, but this can be any command, and it can have as many arguments as you want and so forth. So this can be any arbitrary executable here. We'll step into this, and what I'm going to do here is just call this create templates impl, and I'm going to pass it some of these Xalon objects, the templates impl, the abstract translet, and the transformer factory impl. So let me go ahead and step into that. And we've got some steps here where we're going to create a new translet payload and a new abstract translet, get the name, and here's kind of the fun part. So basically this class we're creating has a field which is going to execute on deserialization. And what that field, what you can put into that field is arbitrary bytecode. So that's why this is a fun gadget to use in an exploit, right? Because it's a kind of one-stop shopping. You just write some bytecode and plug it into this field, and then if you can get the victim to deserialize this object, it's going to execute arbitrary bytecode upon deserialization. So here, all we're doing is we've got some Java code which is going to invoke, get runtime exec. We're going to take the command we put in, which was the calc.exe, and plug it in here as the the name of the binary to run with the exec command, and that's really all it is. And so if we continue here, we set up a couple more fields, and we convert that Java code into bytecodes and plug that into the class using the set field value reflection method. And then we set a couple other fields, return to templates, return back into our RCE payload method. So here we're going to create a series of gadgets. So here we've got a constant transformer, and an instantiate transformer, and we're going to now grab a field, create a chain transformer object and a priority queue, add a couple numbers, and then we're going to swap in a couple values to arm our exploit, and then serialize it. So step into Serialize real quick. Serialize is, basically the 4 lines of code I showed you earlier. Here I just put it into a try with resources block, which makes sense. Try with resources is awesome. And so we'll go ahead and write that object. We'll serialize it. I'm going to convert it to a byte array so I could just do this all in memory. And so now we've got our, here's our gadget here as a byte array. So next, we're going to now serialize the object. So I'll step into this. Step into this. So now we're going to deserialize the object. Again, this is exactly the same 3 or 4 lines of code I showed you earlier. We're going to create the object input stream around this buffer that we created, and we're going to call the read object method. Now again, as soon as I invoke the read object method before it returns, what's it going to do, right? It's going to take this stream, it's going to look for the first object, it's going to go find the class, it's going to resolve it. So you don't have to use that class anywhere in your code, right, for it to find it and resolve it. And then it's going to deserialize it, and it's going to create an instance, of that method as it deserializes it. So it's going to call a bunch of methods, and one of the methods that will get invoked during the deserialization of this particular object is, run this arbitrary bytecode that the attacker supplied. So as soon as I single step here, boom, we get a calculator. And, this works perfectly well, so you and your friends can have lunch and figure out what everyone owes, including tip down to the nearest penny. That's what we used to do at IBM anyway, because we were geeks. Okay, so that's pretty much it for this demo. I just suppressed the exceptions here. If you get a little fancier, you can wrap this in some additional objects so that the exceptions don't show up and there's less indication to your system administrator in the logs that any sort of attack occurred here. And you do get some warnings here. I'm running JDK 12.02, so I just downloaded this, last Friday. So this is the latest version of the JVM. You do get some warnings from the modular system here during the creation of this exploit, but I don't think you see anything during the actual deserialization of the exploit. Okay, so let's go back to the slides. I have another quick demo coming up that's not as visually interesting, but I'll show it to you anyway. So DOS attacks are very simple. There's a really nice one, and by nice I mean just horrible, that was developed by Walter Kolkertz. And this really succeeds against any Java application that allows deserialization. So he defines a hash set with cycles. So deserializing the hash set basically recurses indefinitely, consuming CPU. So it's a really good denial of service attack. If it were an out-of-memory issue, eventually you'd get an out-of-memory exception that you could potentially recover from, but this is just going to make your process disappear forever. So I'll demonstrate this really fast. Let's see here. I put this little hint here so I know which one it is, and sometimes I forget to look. So this is SER06J. It's down here. Okay. So I'm just going to show you what this code looks like because the actual run here is kind of boring. So here's the DOS payload. So we create a hash set, we create another hash set, and then we loop for 0 to 100, and we assign some hash sets to the other hash sets and add them to each other and just kind of create this cycle, I assume. So the main here creates a thread, and then it serializes the DOS payload, and then it deserializes the payload. And so meanwhile, while this thread is running, I'm going to just wait 10 seconds, because 10 seconds in computing time is an infinite amount of time. I think we can all agree on that. And then exit. So if you see the exiting and you don't see the deserialized, it means that this loop is still, this deserialization is still running. So I'm just going to go ahead and run this. And exiting. Yeah, so basically, this thread here will run until the sun burns out, and the reason, of course, I don't just run the DOS attack is it's pretty successful, so I have to work really hard to get the mouse to go over to the stop button to stop execution because it's burning through all your CPU. Okay, so back to the slides. Okay, so another kind of attack. Apache Commons has an object called file upload. There was a CVE for this in 2016. And I guess I'll say here quickly, there's a bunch of known gadgets, and the typical defense is let's come up with a deny list or blacklist of known gadgets. And then we've solved the problem. And of course, no, you've not solved the problem. There's basically an infinite number of gadgets that can be used in an exploit. So it's not a numerable set. So trying to create a deny list or a blacklist of gadgets to protect against is not a solution. So, there's a couple gadgets that get picked on, and I feel bad for the Apache people. Uh, it's not just their problem. So anyway, this library has a disk file item class that handles file uploads, and it's serializable. It does implement customized write object and read object methods. And so this allows remote code execution and file manipulation. And this actually occurs on the invocation of the finalize method, which is sort of extra special fun when you think about it, because the finalize method runs in the garbage collector, which is a separate security context from actual deserialization of your object. So that's a fun way to get burned. So this particular vulnerability, this object allows an attacker to delete a file upon deserialization of malicious input. Basically, all it does is during finalization, it says, let me get this file and delete it, right? And of course, the problem here is that the attacker is in a position to specify the name of that file. So they can just kind of pick an arbitrary file on your system they want to disappear. And when this object that they give you, which again, you probably weren't expecting this object, gets deserialized, that file gets erased. And so basically, when you're looking to prevent against these type of attacks, what you're protecting against is any code in any class if it runs on arbitrary data supplied by an attacker, right? And that's how this is how this becomes a very intractable problem, to deal with it, say with deny list, right? Try to find all those classes, right? And they're not only classes that you're actually running, right? They're classes that are available on your class path, right? So it could be in a library that you didn't even know was sitting on your class path somewhere, and it could still be, if it can be found by resolve class method, the attacker can use it in the exploit. Okay, so risk factors, the biggest one is, is the data you're taking deserializing trusted or untrusted? And of course, in the security field, the one person, the group of people you can't trust, you should trust the least is your users, right? Again, deserializing an object, putting it on your client's system where they can edit that, and then later on retrieving that, that's quite prone to exploitation. So does deserialization take place before authentication? Again, that only helps if you can trust your users. If your users aren't trusted, then that's still an issue. And more importantly, is there any sort of limit placed on which type of object can be deserialized? So basically, is there some sort of allow list in place? So, a question is, does the deserialization host have gadgets available that can be used in an attack? The answer is yes, absolutely. I don't need to look at your system. They are available. They are there. So the primary mitigation, I wanted to talk about look-ahead object input streams, and if I get this anywhere near any NCC group employee, they'll say, make sure you tell them just not to do this. Right? So this is basically the warning. Just don't deserialize untrusted data. But look-ahead deserialization or look-ahead object input streams can be used for both allow listing and deny listing of objects. There are a bunch of existing off-the-shelf solutions. The one I like the most, and probably the one everyone here likes the most, is JDK Enhancement Proposal 290, which was shipped as part of Java 9. There's also some other solutions, Serial Killer. Apache Commons has a solution. validating object input stream, which is kind of ironic because that same library has all these gadgets that you'll use in your attack. And contrast security has a solution. So this whole, this whole approach of Java serialization filtering is to let you look at what objects you're going to deserialize before you start to deserialize them. So you can kind of look ahead into the stream and see if there are any questionable classes there. So again, the purpose is to narrow the set of deserializable classes to a context-appropriate set of classes. So context-appropriate means every time you deserialize, you can decide what sort of objects you want to deserialize in that particular case. So these solutions typically also let you filter for graph size and complexity to validate normal graph behaviors, right? So one of the things about that Walter Kochert's denial of service attack, that used one object and was about 53 bytes in size, right? So that denial of service attack is so small and so simple that you can't set limits small enough to allow deserialization of actual objects and prevent that attack. So, the filtering for graph size and complexity, for the most part, I would say is ineffective solution. So JP 290 still has that. You could use it if you like, but don't depend on it for your security. It's not going to prevent these attacks. It also provides a mechanism for RMI exported objects to validate their classes in a set of expected classes. It doesn't require subclassing or modification of the object input stream subclasses. So Java 9 and later versions support process-wide filters, custom filters, and built-in filters. The core mechanism for this is a filter interface that's implemented by serialization clients and set on the object input stream. The configurable process-wide filters were backported to 8, 7, and 6. And so, the process-wide filters are basically a kind of a very kind of broad hammer where you just kind of say, I'm going to set this whitelist for my entire process, which means you've got to look at every place you deserialize and create sort of a superset of objects that you're willing to deserialize. So it's kind of a, I'm still missing the word, but it's kind of a gross solution. It's a little bit unwieldy. Custom filters let you, only whitelist or allow list the precise objects you want to allow. So process-wide filters are configured via system property or security property value. If the system property is supplied, it supersedes the security property value. So the system property is JDK serial filter, and the security property has the same name, and it's configured in security Java properties. So again, the custom filters are written by implementing the object input filter interface and then overriding the check input method in the Java deserialization. So the object input stream class starting with Java 9 added two methods to both set and get the current object filter. So you could retrieve the existing one and replace it with a new filter specific to that deserialization effort. You can also set filters with config set zero filter, which will affect every object input stream that doesn't otherwise set a filter. And if there is no filter set, then a global filter is used if it's defined. So I'm actually finishing, which is remarkable. I tried to make this one short so I could finish everything and not like run over and then start talking faster and faster as it went along. So again, and I succeeded. So the primary mitigation is not to deserialize untrusted data. In cases where deserializing untrusted data can't be avoided, you can use a look-ahead object input stream to only deserialize necessary classes, and then apply a custom filter with an allow list or a whitelist for each particular use of deserialization. It's a good idea to use a security manager and security policy. You know, you might as well try to reduce privileges as much as possible before allowing an attacker to execute arbitrary code on your system. But again, don't count on the security manager to prevent all the possible attacks that might take place. So it's not an adequate solution by itself. So data channels or streams used for deserialization should be authenticated, or you know, another thing you can do is actually encode and sign the serialization streams. That starts to get you into, you know, cryptography, and that gets you into keys, and that gets you into key management. So it's sort of an unwieldy solution if all you're doing is using it for deserialization. If you already have this problem, then it might not be a bad idea to you know, sign and seal these deserialization objects as well. So that's all I have. I guess that means I can take questions for a few minutes. Anyone have any questions? Yeah, sir. I think you should stand up to the microphone, perhaps. Oh, really? Yeah, why not? You know, they're filming it. People can hear you, all that.
All right. My question is, well, sometimes it's kind of almost unavoidable to use serialization in certain scenarios that I've come across because of, you know, the way you have to integrate with what you have, the frameworks and everything. So I just want to make it patently clear that if we use a filter like you showed there, and we know exactly what's going to be deserialized. For example, we know, an example that comes to mind is the Apache HTTP client actually allows us to have a persistence, to persist cookies, basically. And the way it does it is by giving us the actual HTTP classes that represent cookies. And we know what goes in it. It's like a bunch of strings, a bunch of ints. And so if we whitelist only those things, it's completely safe to use Java serialization.
Yeah, completely safe is a strong term, but you know, so basically the way you do Java deserialization of untrusted data is that you create a allow list of some very small set of objects, and then what you have to do is you have to, you know, examine all those objects and see how they're coded and see what sort of behaviors you know, they have. And the 8-hour version of this, I go through how to do that, right? And so there's a lot of, you know, you have to have a really good understanding because there's 3 or 4 different types of attacks I didn't describe in this talk, you know, and so you know, there's other types of callback methods that you need to implement to make sure they're secure. If you have very simple objects with no invariants, it's pretty easy to do it securely. But when you think about it, as soon as there's an invariant, you have to maintain that invariant during deserialization, which means you have to execute some code to do that, and then you have to be concerned with what that code does and how it could be abused. So it's, you know, theoretically possible, but it's very challenging.
Do you consider like serializing the thing to JSON is safer?
To what?
To JSON.
Oh, to JSON. Yeah. You know, I'm going to say no. Right. No. So I have a 50-minute talk on you know, deserialization of JSON Jackson in Java, yeah. And what people say is that by default it's more secure, or it's secure, and that's true, but basically the 2 things that you have to enable to make it insecure are things that everyone enables. So basically what you need to enable to make it insecure is polymorphic type handling. So if you're going to deserialize subclasses or abstract classes, you have to enable this. And once you enable it, now you're susceptible to attack with Jackson JSON. So I would say it's not really more secure. And basically every one of these technologies in Java, C#, other languages, there are researchers out there showing how they can be exploited. So things like Google protobufs, I don't know of any way to exploit that. I haven't spent any time trying to do it. So I wouldn't say it's safe until I had a chance to break it. But basically, what you have to think about is there code running because I'm deserializing an object? And if there is, you've handed control to the attacker to decide what code is executing in your JVM, and that's where the danger is.
Right. So, if nobody, sorry, just JSON. What do you think about JSON?
Oh, JSON?
Yeah, the Google JSON deserializer. Because we seem to trust it quite a lot where I work.
Yeah. Let me check and get back on you. I gotta look at my little chart of things I know are exploitable and not exploitable and stuff like that.
That'd be great.
I haven't thought about that in a little bit. Anyone else have any questions? No? Okay, I guess we're done. It's six. It is. I am ending. Actually, I ran a minute late. So, thanks again for your time today.